In this video, you and I get to take a look at creating the virtual routing and forwarding instances, one per customer, on each of our PEs that support those customers. Let's jump in. Here are the opt-out questions for this video. So take a moment, read the questions. If you know the answers and are comfortable with these concepts, you can go ahead and jump right to the next video. Otherwise, let's begin. I'd like you to imagine that you and I are going to the mall. We're going to go do some shopping, and as we walk in, what's one of the first things we see that's right there up in front as you walk into a mall? And what we're often going to see is a big map that shows us where all the shops are and the names, where the restaurants are, and very likely it's also going to have a little dot saying, "You are here," to give you an indicator of exactly where you are on that map at that moment. Well, what you and I get to do is we're going to use this map right here for two things. Number one, we'll use it to review the process of building the control plane in an MPLS Layer 3 VPN solution. And secondly, we can use it as we talk about the ingredients that go into a virtual routing and forwarding instance on one of our PE routers. So let's start with their route that's being advertised by Acme Site 1. Let's say it's the 172.16 something network, and it's being advertised via a routing protocol. Let's say it's OSPF. Now, in our map, we would be right here at point A. An IP version 4 route is sent from the CE, the customer edge, to the PE, the provider edge. In this case, that's R1, the provider edge. And when the route comes in, it's received on this interface. In the case of R1, that's interface 2/0, and that interface is going to be assigned to the VRF, that virtual routing and forwarding instance associated with the Acme customer. And in our map, that would be right here. That route of 172.16 is received on the interface associated with that customer's VRF. So the route is not in the global routing table on R1, rather that route is in the VRF routing table for Acme. The next thing that's going to happen is router 1 is going to take that route out of the VRF and export it into multi-protocol BGP as a VPN v4 route. And that's this point right here in our map. So if we were going to take a look inside of BGP at that VPN v4 route, it would look something like the original network, 172.16.00/12. That's also often referred to as the prefix. It's really just the network. It would include whatever VPN label that R1 has associated with that route. So R1's using an address space of 100 through 199. So let's say the VPN label is 125. I'm just making that up because I haven't asked R1 what the label is that he's dynamically going to assign, so we'll just say it's 125 for the moment. That route is also going to have the route distinguisher. See, associated with the VRF for Acme, there's going to be a route distinguisher. So on R1, if we use the route distinguisher of 1.1.1.1:1, and the route distinguisher could be either the autonomous system number, colon, and some other number, or it could be an IP address, colon, then some other number. It just depends on how you want to set it up and what kind of numbering system you want to use. But if R1 for the Acme VRF was using this route distinguisher, it would also have that route distinguisher of 1.1.1.1:1 as part of that VPN v4 route. And that route distinguisher is actually literally part of the network layer reachability information. So it's not just 172.16.00/12, it's also route distinguisher 1.1.1.1:1. And the goal of the route distinguisher is to keep routes inside of multi-protocol BGP to keep them unique and different. Because the route distinguisher is different for each of our VRFs. For example, CBT may be using 1.1.1.1:2. That difference right there in the route distinguisher, that would keep separate, for example, a network of 172.16.00/12 that Acme was advertising, which would be different from the 172.16.00/12 that CBT is advertising. So as a VPN v4 route, the route distinguisher is going to guarantee uniqueness even when our customers happen to be using the same identical network address space. The other thing that would be included as part of that VPN v4 route, in addition to the VPN label, the route distinguisher, would be something called the route target. And it's really simple. Let's say we're pulling this route out of the VRF called Acme. And let's say that the export route target for Acme on R1 is 1.1.1.1:101. Now, this could be the autonomous system number, a colon, and then some other number, or it could be an IP address, a colon, and then some number. In this case, I'm just using the loopback address of R1 as an identifier, followed by some number. I chose 101 as the export route target for the Acme VRF. Now, when this route is exported out of the VRF, it's going to add on this export route target value. So I'll put it right here, route target, and it is 1.1.1.1:101. And that is an extended community value in BGP. So what started off as this one network now ends up as a multi-protocol BGP VPN v4 route with all of this information associated with that route. I'd like to pause just for a moment and talk about exported versus imported. What does that mean? If we're exporting it or we're importing it. I want to share with you a really easy way to remember exactly what that means. Everything regarding exporting or importing is in regards to the VRF. So I'd like you to draw this out with me right here. Draw the VRF with a little circle around it, and then I'd like you to draw a line that says export, meaning you're taking routes out of the VRF and putting them into something else, like BGP. And import is a line going into the VRF. So if you draw this simple little diagram right here, it'll help you remember when we say the word export what we're really doing. We're taking a route out of a VRF and putting it into, and I'll put over here in parentheses, multi-protocol BGP. And on some router, if we're taking routes out of multi-protocol BGP and we're injecting them or adding them into a VRF, that, my friend, would be an import. So if we go back to this step right here, as we export routes to BGP, we're taking them out of the VRF and into multi-protocol BGP as VPN v4 routes. That's when we're going to have all these details associated with that VPN v4 route in BGP. Now the next step is a lot of fun. Inside of our service provider network, we are going to advertise that VPN v4 route to any of our other BGP neighbors. And we might have a network with lots of BGP neighbors and or some route reflectors if we have a huge network. But the end result is we're sharing those VPN v4 routes with the other provider edges that need to have those routes. So in our case, R1 would have this internal BGP session between R1 and R5 that would be supporting VPN v4 routing information that can be shared between those two devices. And then when R5 sees this VPN v4 route, how does it know? How does it know, oh golly, should I take this route and should I import it into the VRF for Acme so I can then forward it up to the Acme site too, or should I not import it into the VRF? And here's what R5 does to make the decision, should I import or should I not import? It looks at this value right here, the route target. And it's really quite simple. It looks at the route target and it says to itself, for my VRF for Acme, which I'll go ahead and highlight right here in pink in this column, if in the VRF that R5 has configured for Acme, if the import route target is 1.1.1.1:101, and if that import route target matches the route target that's part of that VPN v4 route, that, my friend, is the magic that causes R5 to say, it's a match, it's a match. The route target in this route matches the import route target in the VRF for Acme. I'm going to import it. So it takes it, and again, take a look at the import here. It's going to take it out of multi-protocol BGP. It's going to import it into the VRF on R5 so it can then advertise that IPv4 route of 172.16.0.0/12 up to Acme Site 2. And that's these last two steps right here. We import the route from multi-protocol BGP based on the route target being a winner or matching. And the last step is that we're going to simply strip off all of the extra stuff. For example, we're going to strip off any kind of route distinguishers, any type of VPN labels, any type of route targets, and simply advertise a plain old IPv4 network, a prefix, via a routing protocol like OSPF or RIP or EIGRP up to Acme Site 2. And then Acme Site 2 router says, gee, I now know how to reach the network 172.16.0.0/12. My good buddy R5 told me. I'll use him as the next hop. It's now in the routing table on Acme Site 2. Now, Abraham Lincoln once said regarding MPLS Layer 3 VPNs, if you have 6 hours to cut down a tree, you should spend 5 of those hours in sharpening your axe and in implementing MPLS Layer 3 VPNs. And when we're creating these virtual routing and forwarding instances on R1 and R5 on our PE routers, it really is important to plan ahead regarding what you're going to use for the names of the VRFs, what the route distinguishers are going to be for the VRFs, what the export and import route targets are going to be regarding your VRFs. And you'll also want to plan out which interfaces on your PE routers should be allocated or dedicated to that specific VRF. And that's important because any routes that we receive on a given interface, we're going to assume, oh, these belong to this customer because this interface on my local router belongs to that same VRF. So let's take a look together at our game plan for implementing our VRFs on R1 and on R5. So here's the column for the values that we're going to use on R1. Here's the column for the values we're going to use on R5 respectively. Now regarding a VRF name, let's start with Acme. We are going to use 101:Acme. Now you can come up with any kind of a naming scheme that you want to for the VRFs, and you don't have to have them match. For example, we could call the VRF for Acme over here, we could call it Acme 1 on R1, and on R5 we could call it Acme 2 based on the sites. It's just a name, it's locally significant, but it is case sensitive. So if you use uppercase for Acme here, later in the config when we refer to that VRF, we need to make sure we have an uppercase if that's the way we created it. And for CBT, we'll use 102:CBT on both R1 and R5. So if we have 15 different customers with multiple sites each, we would have 15 different VRFs created on the PEs supporting those customers. Next, we need a route distinguisher. Now the format for a route distinguisher is the ASN : and then some number, or it can be an IP address and then some number. So in this case, for Acme's VRF, I'm going to use the route distinguisher of 1.1.1.1, which is the loopback address of R1, :1. And for R5, for that same VRF, we're going to use 5.5.5.5:1. Now, the route distinguisher, we could have used the exact same route distinguisher for Acme on R1 and R5. The same exact number. That's allowed if you want to. So in our network, we are going to use different route distinguishers for the same VPN for Acme on R1 and R5, although many examples that you'll see will have the same exact route distinguisher on both sides for that same VPN. In this case, the VPN for Acme, and that's perfectly acceptable. And for CBT, we're going to use 1.1.1.2 on R1 and 5.5.5.5:2 on R5. So on the VRFs that we create for R1 and R5, we're going to have a name, and that doesn't have to be the same on both R1 and R5. We're going to have route distinguishers that can be the same but don't have to be on R1 and R5. And then we're also going to define route targets. So let's say, for example, that this network, 172.16.0.0/12, we want that network to be advertised so that Acme Site 2 knows about that route. So at this point in the game, right here, when the route is taken out of the VRF and put into multi-protocol BGP as a VPN v4 route, because it's an export, it's going to take whatever the export value is as far as a route target, and that's the route target that's going to be associated with that route. Now the reality is you can have multiple route targets because they're just extended community values. You can have multiple route targets associated with a VPN v4 route. In this example, as a route comes out of Acme on R1, it's just going to have a single route target being assigned, and that's 1.1.1.1:101. Now this could be an IP address and then a number, or you could use your autonomous system number and then a number. It's up to you based on how you want to set it up. And here's how that export route target comes into play. If we want that route of 172.16.0.0, which has the route target of 1.1.1.1:101 associated with it in BGP, if we want R5 to take that and import that route into the VRF that it has for Acme, we need to make sure that on R5, on its VRF for Acme, that it has an import route target that matches the route target associated with that route. So it's no accident that the export on one side is going to match the import on another, because that's the magic of controlling exactly which routes get shared with which other VPNs. Now, if we got the route targets incorrect, and for example, we exported a route into BGP from Acme, and we actually exported it with 1.1.1.1:102, and that would be a big problem because that route target matches the import route target that R5 is going to use for routes that it needs to give over to CBT at Site 2. which is this guy right here. So the key point is that route targets control exactly where those routes are going to be shared. It's not the route distinguisher, it's not the VRF name, it's all about the route targets themselves. A lot of examples that I've seen with route targets in documentation simply show a route target, for example, for Acme of 1:1 for export and for import. And if we did that for Acme's VRFs anywhere they existed, for example, R1 and R5, we used a 1:1 export and a 1:1 import. And that would work because the routes, when they're exported from that VRF for Acme, would be labeled, if you will, or tagged with a route target of 1:1. And R5, when it's importing routes into the VRF, if it's looking for 1:1, those routes will be brought into the VRF and subsequently advertised up to Acme at Site 2. And with the same numbers used all the way around for Acme, it would work in the other direction as well. The 192.168 network, as it's exported into BGP, would have a route target of 1:1. And on R1, when it sees a route with a route target of 1:1, if that's the import route target as well, on R1, that would cause it to be imported and then advertised up to Acme at Site 1. But I think it's really important for learning purposes to actually see the relationship and make them different so that you realize exactly what that route target is doing. So if we combine the route target information with the example of a VRF and importing and exporting to remind ourselves of which of those route targets are going to be used, for example, the export route targets would be used at point A and the import route targets would be used at point B to control whether or not a specific VRF would be able to get those routes from multi-protocol BGP. Regarding interfaces, what we need to decide is, on R1, for example, which interfaces are going to be assigned to and allocated to a specific VRF on R1. So in the case of Acme's VRF, it's very likely we're going to assign FA2/0 on R1 because that's the interface where we'll be learning about routes from that customer and also sending routes to that customer. So on R1, we'd use FA2/0 for Acme. And on R5, we'd also use FA2/0 simply because that's how we built out the topology in GNS3. So whatever the interface is that's going to the Acme customer edge, that's the interface that we'd want to allocate and dedicate to the VRF for Acme. And for CBT, we're using Fast Ethernet 2/1, so that would be allocated as part of the CBT VRF. And over on R5, it's also 2/1, which would be allocated to the CBT VRF, simply because that's the interface that connects over to the CBT customer edge at Site 2. I have this table, by the way, available for you in the Nugget Lab files for this video, and that way if you want to have it as a separate document to refer to as you're labbing this up and practicing, it'll be available for you, as well as this topology, which is also in the Nugget Lab files. So with our plan in place, the next thing that you and I get to do is implement the VRFs on R1 and R5 with all of these details. Now there's actually two different ways of creating a VRF as far as the syntax. There's a method that supports just IPv4 only VRFs, and there's another option that supports IPv4 or IPv6. And what I'd like to do is walk you through the method that supports both. So let's start off. We're on the right router. I'm on R1, which is our PE, and we're going to use VRF definition and then simply specify the name that we want to use on this local router for the VRF that we're going to allocate for our customer Acme. Now this right here is the way of doing it to support IPv4 or IPv6. If you only wanted to support IPv4, the command would be IPVRF and then the name you wanted to call it. If you wanted to call it the same name, it would be like that. So we're using VRF definition to go into VRF configuration mode instead of IPVRF, which would also take you into configuration mode for IPv4 only. And I point that out primarily because you may come across or be working with an iOS router that only supports IPv4 VRFs. In that case, you'd want to be familiar with this syntax so you could go ahead and work with it on that version of iOS. Now the next thing we're going to do is we're going to identify the route distinguisher that we want to associate with the routes that are being imported and exported within this VRF. So if a route, for example, is being exported out of this VRF and goes into multi-protocol BGP, it's going to be tagged on with the network layer reachability information of 1.1.1.1:1. And what you and I would want to make sure we do is that on R1, we'd want to make sure that the route distinguisher that we use for Acme, as an example, is a different route distinguisher than we use for CBT or some other customer. Because if two different customers have the same exact route and we're using the same exact route distinguisher, it's going to be really tough for multi-protocol BGP to distinguish those routes from each other, because in that case the IP address and the route distinguisher number would be identical. And the whole purpose of that route distinguisher is to keep those routes looking different as they sit in multi-protocol BGP as VPN v4 routes. Now the next piece we're going to do is we are going to go into a special room inside of this VRF definition, and we're going to go into the room specifically for IPv4. And this is very similar to how we did it with BGP. We're going to use the concept of an address family. So by typing in this command, address-family IPv4, you'll notice that the prompt change, we're now in address family configuration mode for IPv4. So inside of address family IPv4 configuration mode, we can now specify the route targets for both import and export that we want to associate with this VRF. Now, if you're using the older IPv4 only method, you wouldn't have to bother specifying address family IPv4 because it would assume that the entire VRF is just IPv4. So based on our plan, I'm going to say that the route target export is going to be 1.1.1.1:101. So any routes exported out of this VRF into multi-protocol BGP as VPN v4 routes are going to get that little extra information as an extended community value associated with that route. Now the next question is, which routes should R1 pull out of BGP and put into this VRF as an import? And we'll do that with the route target import command. And based on our plan, looking at the table, we want to grab any routes that have a route target of 5.5.5.5:101 and bring those into the VRF. And there's also the option of saying route-target space both, which means, hey, both import and export, and then specifying the route target. And that way you can save a little bit of typing if your import and export route targets are identical. And then what we'll do is we'll exit out of address family configuration mode and we'll exit out of VRF definition mode. Next, we're going to associate interface FA2/0 with this VRF. Now, a few basics that I like to do, you don't have to do, for example, a MAC address, but in a GNS3 environment where I might be doing captures and I want to see the details at layer 2 and layer 3, I usually hard code the MAC addresses so it's really obvious where this frame is coming from. So I'm going to bring up the interface FA2/0. I've also given it a description indicating this is the connection that goes to Acme Site 1. And the question is, what's the magic? What's the magic we need to perform to allocate this interface, to sacrifice it, if you will, to the VRF that we just created? And the answer is, we're going to use the command VRF forwarding and then the name of that VRF that we just created. And it is case sensitive. So if you used uppercase Acme, you'd want to use uppercase Acme here as well. The other thing that's really important to know is that if you had past tense, if you had an IP address configured on that interface, by assigning it to that VRF, it would automatically wipe out the IP address on the interface. So be aware that you're going to have to put in the IP address again if you did the IP address before you did the VRF assignment. And that's no problem. So we're going to use the IP address of 172.16.101.1 with a 30-bit mask on R1's interface, which is FA2/0, and we'll make the customer's edge router, we'll go ahead and assign that a .2 on that same /30 network. And then we'll exit out of interface configuration mode. So that is the VRF creation for Acme here on R1, but we also have a VRF that we need to create for CBT. So while we're right here, let's go ahead and create the VRF for CBT. So we're going to use VRF definition again. We're going to call it 102:CBT. We're going to use a route distinguisher of 1.1.1.1:2 as opposed to .1, which we use for Acme. We're going to go into address family configuration mode, and we're going to set up our route target import and export. So our export route target is going to be 1.1.1.1:102, again based on our plan. And the import route target is going to be 5.5.5.5:102. Now we need to assign FA2/1 to the VRF that we just created, which is 102:CBT. So to do that, we're going to go into interface configuration mode for FA2/1. We'll give it a quick description, which could help us in the heat of battle to make sure we know where that connection's going. I'm going to put a MAC address on that as well for the benefit of my packet captures. We'll bring the interface up, and then we'll assign it to that VRF with VRF forwarding, the name of the VRF, and assign it an IP address. So we're going to use 172.16.101.1 with a /30. And I want to point out something really fun. Check this out. See that interface IP address for the network 101? That network of 101 is not in the global routing table. It's actually part of the VRF called 101:ACME. And this IP address, which is also on the 101 network, isn't in the global routing table. It's in a VRF called 102:CBT. And that's why the router is not complaining. See, normally if we try to put two different interfaces in the same subnet, the router would say, there's a problem. But because these routes and their directly connected networks are not in the same global routing table, they're isolated, it has no problem with that. So let's do some show commands. Let's do a show IP interface brief. So there's our two interfaces with the exact same IP address. And we'll do a show VRF. That'll give us a Reader's Digest version of our two VRFs that we just created. So there's the names of the VRF. There's the route distinguishers that we identified for each of them. They're both supporting IPv4. And that's because we created them in the address family for IPv4. And there's the interfaces that are associated respectively with each of the VRFs. So the command show VRF is one of those that you want to put in your arsenal to make sure you can verify and see which interfaces are assigned to which VRFs, and also what the VRFs are. If you forgot if you used uppercase or lowercase, it'd be a great way to remember what the names of the VRFs are. Now, one other really cool thing is this. Let's do a show IP route that we know and love. Now, show IP route is showing us the global routing table, and you'll notice that the 172 networks are not in the global routing table. If we wanted to see the routing tables for a specific VRF, we need to ask the router politely for those. And the way we do that is show IP route, tag on the keyword VRF, and then the name of the VRF for which you want to see the routes. So here's our command right here, show IP route, VRF 101:ACME, and it's showing us the one directly connected network of 172.16.101/30 is directly connected on FA2/0. So let's save our config here on R1. And what I'll also do in the Nugget Lab files, I'm going to put the commands that I just used to implement these VRFs. I'm going to put these as part of the Nugget Lab files as well. So if you want to refer to those and double check them as you put them in, that'd be a great way to do it. And I would recommend that although you're going to have these commands available in the script I'm going to provide you, I would strongly recommend practicing several times with these commands just to make sure that you know what the commands are, you know how to implement them, and you'll build those skills which are useful for the real world. So next, let's go over to R5 and let's implement and create the two new VRFs on R5 using the information in the table that we discussed earlier. So on R5, we'll go into configuration mode and we'll say VRF definition. We're going to call this 101:ACME for ACME's VRF on R5. We'll set up the route distinguisher. Then we'll go into address family for IPv4, set up the export and import route targets, and that looks great. And as a reminder, if you are using the IP version 4 only option, you would say IP VRF instead of VRF definition, and you wouldn't need to bother adding the address families because it would assume that everything's IPv4. Next, we'll allocate the interface FA2/0 to that VRF. We'll give it a quick description so we can remember where it goes if we look at the config. I'm going to give it a MAC address for the benefit of any packet captures that we might do. We'll bring it up with a no shutdown. We'll do a VRF forwarding to assign this interface to the 101:ACME VRF, and we'll give it the IP address of 192.168.202.1 with a /30-bit mask. And that looks great too. So let's do similar treatment for the VRF called CBT. So we'll do a VRF definition for 102:CBT. We'll go ahead and do a route distinguisher of 5.5.5.5:2. Address family of IPv4. We'll set up our export and import route targets based on our table. We're not just going to remember what it was. We're going to make sure we're getting it correct. One of the challenges I have often is remembering exactly the numbers I planned on using and implementing those. Then in interface 2/1, we're going to bring it up with the no shutdown. We'll give it a description, the MAC address, and then we'll specify that this interface is going to be dedicated to the VRF called 102:CBT with the VRF forwarding command, and then we'll give it the IP address that we want to use on that interface. Again, we'll give it .1 on a /30. So here's my question for you. What is the command that will give us a high-level overview of the VRFs that we've created, their route distinguishers, and the interfaces associated with those VRFs? Do you recall what that is? If you're saying, oh yeah, Keith, I got it. It's show VRF. You are absolutely correct. So you want to make sure that you got the details based on your plan implemented correctly in the configuration. And to my eyes, this looks good. If we want to verify that our IP addresses are configured correctly, we can do a show IP interface brief. It'll show you all the interfaces, even though not all of these interfaces are associated with the global routing table. And if we did want to look at the routing table for a specific VRF, we do a show IP route, tag on the keyword VRF, and then the VRF name that we want to look at. And if you're running iOS 12.x, you won't have this L route here, but you'll certainly have the directly connected route, which is the one that's important as part of this VRF. Now what we're also going to do is we are going to save our configuration on R5 and R1. Let's go double check to make sure they're saved in both places. And we'll bring up GNS3 and we'll make sure that we save our configuration here as well, so that the next time we bring up this topology, it'll have that additional configuration work on R1 and R5 regarding the VRFs and the interfaces associated with those VRFs. Now your topology should look something like this, with these two customer edges on the left and the two customer edges on the right. And now that R1 and R5 have those VRFs for their respective customers, in our next video, you and I get to turn those customers up and get a routing protocol working between the customer edge and the provider edge. So it's really important that you take the time now to make sure you implement the VRFs on R1 and R5 so you can be ready and prepared for the next video. I have had a great time and I'm glad that you joined me for this video. I hope this has been informative for you and I'd like to thank you for viewing.